Okay, I think we can start. Good morning to friends and colleagues from Belgium and Europe, and good morning to friends and colleagues from China. Welcome to the third China-Belgium Science and Technology Exchange Symposium. My name is Ping Zhu. Dr. Qiujun Ying, and I am the moderator of the climate change session. As you can see, we have a relatively tight schedule. If you have any questions, please leave it in your chat. You can do it either in French, Chinese, and English, or even in Dutch. Some of questions will be answered before roundtable discussions. Here now is Dr. Qiujun Ying to introduce the first speakers. Thank you.
Hello, good morning, good afternoon. I'm Qiujun Ying from University Catholic Leuven. And so today we are very pleased to have 9 invited experts to talk about a very important topic, climate change. So we will have 7 talks, each 20 minutes. The first one will be given by Professor Hugo Goss from University Catholic Leuven, and he is a world-leading expert on climate modeling. So Hugo, you have the chair. I will share screen. I think you can share your screen.
So my screen says that the moderator has deactivated the share screen for the participants. So I'm not allowed to share screen.
How to do with advanced share on all participants?
Yes, you can change it to all participants.
Yes. Yeah, can you try it now?
Yes, I can do it now, I think.
Okay.
Okay. You see my screen?
I do not.
Maybe
not yet.
Not yet. Not yet.
Not yet. Okay, let's see. Just
We see on the screen it's written you have started. Oh, okay, we see it now.
you see the slides now?
Yes. Yes.
Okay, good. So sorry for the small technical. So you see the slides with my screen, or the full screen?
Yes, I can see it.
It looks like a full screen.
Okay, so if it's a full screen, that's good then. So yes, so thank you very much for sharing for inviting me to this symposium. So just check, yes, I should be here. So I would like to talk today about modeling, because we all know that climate, or the basis of climate, is observations. This is the kind of iconic figures that we have seen many times now on the global mean temperature evolution that is observed from thermometers. And you see that the temperature was more or less stable in the 19th century. And then you have a first rise in the temperature in the 20s, and then from the 80s a large warming, and now we are at a temperature which is 1 degree warmer than the pre-industrial temperature. I'm sure that the next speaker will give us much more detail about that, but I would like to focus specifically on climate models, because if observations are the basis of climate, we need also theory. And for us, the one of the best way to use our theory is to build climate models, because climate models can be used both to understand the origin of past changes, but also to project future changes. And both are very important, and they are not independent, of course, because to have reliable projection, you need to understand. And if you look at the robustness of the projections, each time we understand well a new process, we can make more reliable projection, more robust projection. And if we do not understand well what is going on, of course, it's harder to give estimates of what would be the future. On the right here, I have shown a classical view of a model with an Earth and kind of grid. But we must keep in mind that the basis of what we call a climate model is really the physics, the chemistry, the biological principle that you have seen at school. Some of them are very standard, very well known. For example, on the physical equation that we use, it's the Newton's second law of mechanics. We have the conservation of mass, the conservation of energy, the equation of states, the radiative transfer law that explain us how the energy is transferred from the sun towards the Earth and how the Earth is emitting energy towards space. That includes the greenhouse effect. So those physical laws, those fundamental equations are very well known, very standard, but climate is not just only those standard equations. We also need to represent the effect of turbulence, the effect of clouds, the effect of all the changes in the composition of the atmosphere, what we call aerosols. So they are small droplets or small solids that are in suspension in the atmosphere that modify the radiative properties of the atmosphere. So in addition to those laws that are very well known, we still have complex processes that are difficult to understand, that are very sophisticated. And in general, in models, we could not solve everything. So we need to make approximation. We could not have all the details everywhere. And even if we make those approximations, the equations are so complex that we could not solve those equations analytically or on a sheet of paper. You could not just say, I have the full equation. I have 3 months and I spend 3 months making some calculation on my sheet of paper. You will not be able, because those equations could not have a solution that you can write like that in a sheet of paper, except if you make very strong approximations. So the best solution is to have a numerical resolution. We could say at this stage, yes, when you develop a model, so you start with the physical principle, you have to make some approximation, and then you solve your equation on a computer. So where do you need observation? You need observation to develop those physical and biological principles. You know how the clouds are behaving. You know you have to know what is turbulence. Then you need observation to be sure that the approximation that you have made are reasonable. But finally, when you have your resolution, you also have to make approximation, because you could not solve the equations on every grid point or every point on Earth. So what we do, and that's the meaning of this kind of figure, is to separate the Earth on many boxes. And you do not have the solution of your equation everywhere. So you could not compute the solution in every point in Belgium or every point in China. No, you have boxes, and so you have an average. And the typical average for climate model currently is 100 kilometers. So it means that you already have quite a lot of points for China, but for Belgium, you may have 4 or 5 points where you compute the temperature or the precipitation or the winds. Of course, because you do not compute the temperature or the precipitation everywhere, you have to make some approximation in your equation, and your solution is not totally exact. And you have to check afterwards that after those approximations, which are related to the physics, but also to the numerical resolution, because with current day computer, we can just afford this 100 kilometer resolution. Maybe in 5 years, it will be 10 kilometers, but at the moment, that's what we can do. So we have to test from observations that everything we do is fine. When we have this model that is developed, again, physical principles, solution, we can make what we call simulations. What is a simulation with a climate model? You have your model, which is a computer code, so lines of codes on a computer, and you need a relatively limited amount of observation. If you have what we call an Earth system model, a model that represents all the components of the climate system, so Earth system is probably a bit optimistic at the word, because we do not represent everything on Earth, but we consider that we represent the atmosphere, the ocean, the carbon cycle, the aerosols. And with this type of model, you need very few observations to perform a simulation. You just need astronomical parameters. You know where is the sun compared to the Earth. You need to have the topography. You know the mountains. You need the composition of the atmosphere. You need the position of the ocean. You need the amount of salt. There's some properties of vegetation. So what we call boundary condition. Basically, your model that you develop, it is based on equation that could be adapted to any planet. And here you need to have the conditions specifically from Earth. And from that, with those few observations, you can make a simulation that should reproduce the climate you observe on Earth. What with the results of those simulations? You have two options. The first one is to test the validity of the model, because you see that it's a complex process from the equation, the solution, the running. You must be sure that what we do is fine. And for that, you need more observations. So that's quite clear that we need observations, but not necessary to make the simulation. The simulation itself is really based on what we know from the system, but we need observation to develop the model and to test the validity of the model, not for the simulation itself. And if you are happy with your model, you say, okay, my model is running well, then you can analyze mechanism and make the projection that we mentioned earlier. You could say, yes, what are the results of those kind of model? And I'm still always impressed by the fact that if you look at the simulated air temperature, so you have a computer code based on relatively standard equation, and then from this computer code, you try to reproduce the simulated air temperature. And if you look at the simulated air temperature on the left, you compare this map with observation, just by a high like that, you will not see any difference. You have the feeling that the model reproduces very well all the details of the structure of the ocean, of course, of the structure of the temperature on Earth. Of course, it is warmer at the equator than the pole, but you see clearly the changes in the East Pacific, the position of the ocean current, the fact that the temperature in Western Europe is larger than in Eastern America on annual mean. However, if you look a bit more in the details, you see that the models are not perfect. In the majority of the region, the models are able to reproduce the temperature with an accuracy of the order which is better than 1 degree, which is quite impressive again. But if you look at the details, in particular in the mountain region, if you look at the Himalaya region, for instance, you see that you can have quite a large errors. On the right, the figure shows the error of the current generation of models. And you see that where you have this very strong topographic gradients, you still have errors of the order of that can reach 5 degrees. And it is really, in that case, a problem with what we call the resolution of the model. If the model is only able to reproduce the climate at a scale of 100 kilometers, it's very difficult to reproduce what is going on in mountains, where a valley can have a different climate than the next one. There are also some regions like close to the southern tip of Africa, where we have very narrow currents, and those currents are difficult to reproduce if you do not have enough resolution, if you are not able to compute enough points in those currents. You also have some errors in polar region, because we know that the physics there is very complicated and we need to improve. But overall, the results are quite impressive on the way the models are able to reproduce the mean state of current climate. Models are also able to reproduce the history of climate. here it's an example of the evolution of the temperature over the last millennium. So in this figure, you have the global mean surface temperature anomaly over the last millennium. So the difference compared to a mean climate. So you see the black curve. You see the black curve. The black curve is a reconstruction of past climate. I will come back a bit on that later. You see that the temperature 1,000 years ago was more or less 0.2 degree warmer than the mean climate of the last millennium. And then you have a gradual cooling to what we call sometimes the little ice age, with slightly colder temperature in the 19th century before the large warming of the 20th century. So you see already on this map that the warming over the 20th century is quite unusual. But if you look at the result of the models, which are the curves in color, you see that the models are able to reproduce quite well this cooling up to the 19th century and the warming. You see also some dip in the temperature. So you have a low value, for example, at the beginning of the 19th century, and we can relate that to volcanic eruptions that modify the transparency of the atmosphere and thus induce a cooling. You can also use the models to assess now the past projection of global temperature changes. So that's always a problem with climate dynamics. So if you want to make a simulation and estimate of the climate of the next 30 years, you have to wait 30 years to test your projections. The reason why we make what we call test on the past, because there you already have the data, but of course you already know the future. But now we are able to assess the past projection of global temperature change that has been proposed in the 70s. And you see that from the black curve, which was of course unknown at that time when the people make a simulation in the 70s. And if you compare the evolution of the temperature that was estimated by the model at that time compared to observation, the large majority of the estimates that have been made with model at that time are extremely close to what we have observed. And in the 70s, the temperature was not rising yet. So you could not just say, yes, it was expected that global warming would occur with that magnitude. This was really an estimate based on models. And you see now that if you assess those projections, already in the 70s, they were extremely precise. This is the reason why the Nobel Committee gave the Nobel Prize, or one of the reasons why the Nobel Committee gave the Nobel Prize to three scientists, in particular 2 climate scientists. And the quote is for the physical modeling of the Earth's climate, quantifying variability and reliably predicting global warming. So in the 70s, they were already able to make a very good modeling of the physical climate, to quantify the variability and make projections that we know that are right now. So analyzing mechanism, it's something that you can do, but you can also in model play like a kind of virtual world. So you could say, yes, the reality, that's here the black curve, the temperature was stable, or slight rise, and then a large rise over the last decades. But you could not say, yes, what is the exact cause? You cannot make tests. But in a model, you could say, let's imagine I make a simulation with all the forcing, including the human perturbations. And you see that the models are able to reproduce very well the observed changes. The agreement with modern models is extremely good. But if you make the same test only with natural forcing, so you say, okay, imagine a world where the humans were not perturbing climate. In that case, you have a relatively good agreement until the 50s, and then the curves start to diverge. And already in the 90s, you are too far away from the observation, even if you take into account all the sources of uncertainty to explain that this warming could be due to only to natural processes. So that's one of the evidence that proved the IPC, that lead the IPCC to say, yes, it's unequivocal that human influence has warmed the atmosphere over ocean and land over the past decade. So models is not the only way to prove that, but that's a wonderful tool to go in that directions. And I skipped this part because I think I'm already a bit late. But we have to be careful that human activity is not the only thing. So if you make the same story and you compare here now for precipitation, so just take the figure on the left, on the bottom left. If you take the precipitation average over 60 north to 90 north, and you have the same, you have the observation in black, you have the models driven by natural and anthropogenic forcing in orange, and you have in green the natural forcing only. So you see that if you look at the model response, so the response to anthropogenic forcing, you see that you have an increase in precipitation because we expect that there will be more precipitation at high latitude in response to global warming. The model says, yes, this is that kind of behavior that we should expect. But if you look at the observation, you have this kind of warming, and the light orange curves give you the range expected by models. So you have also a lot of natural variability, a lot of uncertainty on precipitation, and we have to continue to understand this variability, because what we will get in the future is the impact of human activities plus natural variability. And to understand this variability, a good way is again to look at the past. And here is a reconstruction that we have made in collaboration with some colleagues over China. So it's a reconstruction of precipitation in the 17th century. That was a very large drought, and the special characteristic of this drought, it was in the northern China, it was very dry, while it was wetter in the southern part of China. So the spatial structure of the precipitation changes at that time was not like, yes, homogeneous drought, they were kind of dipole, and we were able to understand the role of the ocean circulation, the role of the wind in this natural variability, because it's important to continue to understand this type of processes. So as a kind of summary, it was very quick, and in 20 minutes, it's hard to go in all the details, but I wanted to illustrate that climate models are really an important tool in climatology, in climate dynamics, to understand the change, to detect anthropogenic climate change, describe natural variability, projections of future change also, even though I did not have much time to do that, but I'm sure Rafik will give you more details about the future changes in the next talk. Thank you very much for your time.
Thank you very much, Professor Goose. I'm sure that there are many questions, and we will answer the questions during the roundtable discussion. So now we will go to the next speaker.
Thank you very much.
Production, yes.
Yes, thanks again. Yes, this is a very interesting talk. I believe we will have several questions about what you have just presented. So here are the next speakers. It's Dr. Rafik Hamidi. He is a member of the International Association for Urban Climate and also a member of the Urban Climate Change Research Network. He also is also a co-author of IPCC report in 2019. Now the floor is yours, Dr. Rafik.
Thank you very much for the nice introduction. Can you see my slide?
Yes, I can see it.
Okay, perfect. So yes, so I think the previous talk of Hugues was very good. So it will help me a lot for my next present. Thank you very much, Hugues. So it's wonderful. So I will give you an insight about what is happening for the global climate now, so the state of the global climate. And yes, for this I will use the latest report, IPCC ER6 report, where I was involved as lead author. So just some numbers here to start with. So you can see that we are still 234 authors, lead authors. We are from 65 countries. Yeah, IPCC try always to have the gender balance, so 28, so not yet at balance, but yeah. And yes, what is good is that we are also 30% new to the IPCC, so including myself, I am new to the IPCC. So IPCC always also try to involve new scientists and early career scientists. What is also important is that if you look to the number of scientific publication that has been assessed is quite a huge number. You can see here 14,000, and you need to add on top of this the review comment that we got to for the writing for our draft, the different drafts. So you can see that it's an immense number of comment here, more than 78,000 comment that we need to take into account. So it's really a lot of, it's a huge work. So I can maybe give you an example of what I did in the beginning when I start working with the IPCC. So just to write like one page on a specific topic. So reading maybe like an amount of more than 100 paper. I need more than 4 weeks just to write like a page, yes, of text concerning a topic which I am more or less expert on. So it's really a lot of work. So yes, so this is a bit. I wanted to start with this to tell you how we improve, let's say, in the IPCC, and for example, what is new now with respect to when we start in 1990. Yeah, so as you can see, 1990 here to the left, the human influence on climate was still suspected, and so this was clearly still suspected. So it was not clear established, but now it's an established fact. And yes, the mentioned the term unequivocal that humans are influencing the warming the atmosphere, land and ocean. And I must say that this term unequivocal was not so easy to approve with all the government. So it was really, well, I'm happy that at the end, because I was also involved in the approval session, and it was not that easy to accept this term. But at the end, yeah, all the government accepted. Yes, so maybe some, I will not go into detail, but for example, for the observation, so in 1990, so we had a warming from 0.3 to 0.6 degree, and now, yes, the warming is 0.95 and up to 1.2 degrees Celsius. What is good is as Hugues explained very well, is the number of stations that was used. You can see here the number of land surface temperature station that was used when we did this first assessment in 1990. 1,887 stations, but you see now that the number of stations is up to 40,000 stations that has been used. So a big increase in the number of stations that has been used for the assessment. Also, you can see here that we have also satellite remote sensing that has been used, and we have now much more products than what we had in the past. Concerning the models, the climate models, and to make a link with what Hugues presented before. So you can see here that before 1990, our assessment were based on global climate model, as very well explained by Hugues. And at that time, the resolution was still 500 kilometers. So, and now, as Hugues said, so we are going to, now we have a resolution global of 100 kilometers. And what is also good is that IPCC is using also a regional climate model. So this is a model that can focus on a region. That's why they are called regional. And of course, when we only focus on one region, we can use all the computing power to increase the resolution. And here you can see that we are between 25 and 50 kilometer resolution. And of course, also process has been, some physical process has been improved now that was not included in the previous version of the global model. Yes, so what IPCC tell us now is that we have a recent change in the climate. So the recent change in the climate are widespread, rapid, and intensifying, and unprecedented in thousands of years. And global temperature over the past 10 years was about 1.1 degree warmer than in 1850, 1900. And as presented by each of the past 4 decades has been the warmest on record since pre-industrial time. Yes, what we learn also is that unless there are immediate, rapid, and large-scale reduction in greenhouse gas emission, limiting warming to 1.5 degree will be beyond reach. In fact, the CO2 concentration in 2019 were higher than at any time in at least 2 million years, and concentration of methane and nitrous oxide were at their highest in at least 800,000 years. Yes, now, and this is really a new finding from this report with respect to the attribution. It's really indisputable that human activity are causing climate change, and they are making extreme climate events, including heat waves, heavy rainfall, and drought more frequent and severe. And this is due to a new attribution method that has been used in this latest report that allow us to link more clearly the human activities to the extreme events that are happening all over the world. Yes, and I said climate change is now already affecting every region on Earth and in multiple ways. And of course, this change that we experience will increase with further warming. So every 0.5 degree of warming can have a big impact on the change that we are expecting. Since 1950s, heavy rainfall events have become more frequent and intense over most land area where there is sufficient data to see a trend. And you can see again here the benefit of having observation, so in a certain region. Yes, and human-induced climate change is also contributing to increase in drought in some regions. And as you know, there is no going back from some change in the climate system. So even if we stop all emission this afternoon, some change related to ocean, for example, will not stop. So and we so the warming will still be happening even if we stop the emission because of the big inertia of this change that are a really slow process change. So especially if you look to the ocean, you have the ice sheet, you have the sea level. This change will still continue for thousands of years, even if we stop the emission today. Yes, so here just to give you an order of, to have an order of magnitude of this. So in fact, if we stop sustained reduction in carbon dioxide emission will become, so if we stop the emission, we will need about 5 to 10 years to see the impact on CO2 concentration in the atmosphere. But then we will need between 20 and 30 years to see the impact on global surface temperature. So just to give you some order of magnitude of the time needed to have this. So as I said, to limit global warming, strong, rapid, and sustained reduction in CO2, methane, and other greenhouse gas are necessary. This would not only reduce the consequence of climate change, but also improve the air quality. Yeah, so here, why CO2 is the dominant greenhouse gas and reaching net zero CO2 is required to limit global warming. Strong reduction in other greenhouse gas emissions are needed, and such as methane. Among these, we have methane reduction together with strict air pollution control, which benefit both the climate and improve also air quality. And I will show you later one example concerning urban area. Yes, so here I am just showing the impact of climate change on hot extremes. And what is the confidence on human contribution to this observed change? So this is you can see that. So this is a map which is considering the world, if you want. So we have these boxes here, So the line of the color of the box is so if it's red here, it's increased. So you can see that all over the world, except some region here, for example, Central Africa, but this is due to limited data, we are experiencing an increase of the hot extremes. Now you can see for Western Europe here, also for China, Eastern here, we can see this increase. And the dot here, the black dot here, we have sometimes we have 3. This is our confidence in the human contribution to this observed change in hot extremes. So if we look to, for example, to Western Europe here, WCE here, Western Central Europe, you see that we have three bullets, this means that our confidence is high. So we have a high confidence that the human contribution on human contribution to this observed extreme, hot extreme. The same is here. If you look to Eastern Asia here, you see that we have also 3 bullets here, meaning that we have high confidence on this change. Yes, and I would like just to have a dedicated here on urban, because this is my topic. So I would like to share with you the latest finding on urban area. So why we are interested on urban? Because cities are on the front line. Because yes, by 2030, almost 60% of the world's population is projected to be living in cities. So we need to focus on this, and the majority of this increase in population will be happening in developing countries in Africa and also in Southeast Asia. So in South Asia, and yeah, so it's So we need to be careful to and when we are building, for example, when we build cities or when we are doing new building, so the time scale of for building is more or less the same as climate change. So it's more or less 100 years. So we need to take into account what climate change is can affect the urban area and the building. So here what we did is, so we try to see this urban heat island. So what is urban heat island is the fact that if you are in the cities are in general warmer than the surrounding. And this order of magnitude can be up to, sometime up to 10 degrees for big cities. If you have like clear sky and anticyclonic situation with the low wind, etc. So during the night, the city will be warmer. And we wanted to know what is the main factors that that influence on the establishment of this urban heat island. And we did this for all over the world, looking to the available literature, so the different cities all over the world. So what we found is that, so here, what is red is the warming, and what is blue or yes, green is for the cooling. So what we found is that the city geometry, so this morphology of the city, so for example, the building density, so it's really the 3D geometry, how we are building city with narrow street, with wider street. So this is the main important factor that established the urban heat island. And you can see that the warming is, you can see here that we have almost the same order of magnitude such as the global warming. You see here it's more than 1.2 degree here of warming. And so here this hashed line is with respect to different background climate. So of course with different background climate we can have different so we have this uncertainty related to different climate zone. But you can see that the main important factor is the city geometry. And of course, if we would like to have cooling, the main important factor is the vegetation. You see here that the cooling can go. So we can, if we have a smart combination of city geometry and vegetation, we can cancel, we can offset this urban heat island in cities. This will help a lot with, yes, under future climate change. Yes, the impact on precipitation. So the city don't impact only temperature, but also precipitation. So we found that urbanization with time alters the water cycle, generating increased precipitation over and downwind of the city with medium confidence. And with high confidence, we found that this will increase the surface runoff intensity. And it's very clear also during the flooding event that we had here in Belgium and also in China, the fact that you are in a city, you will, the surface runoff will be much more important due to the impervious area, etc. in the city. We have other impact like for humidity and wind, but we still have not that much evidence on impact. But of course, I mean, on the long term, if you for observation on year, or we can find this effect on wind, but we are missing observation on long term. And this is also a very important aspect, that for cities, we are missing long-term observation. So, yeah, so what is the observed trend here? Sorry. So we found that, yes, of course, despite having a negligible impact on global annual mean surface air warming, so the urbanization will, of course, will not impact the global warming, but it will exacerbate the warming, the global warming in cities that has developed in the past. And here what we did, we tried to find for some cities where we have observation, what is the percentage of urban warming and what is the percentage of global warming that has been observed by stations, so from observation. So you can see, for example, here for Brussels, we did this exercise. We found that 0.62 degree of the warming is just driven by increase in Brussels. So Brussels become bigger and bigger, and the observation that here in Uccle was observing also this increase of the city and the increase in urban heat island. So and we did this for different cities. We did this as an average over China. You see here that almost 0.5 degree is due to the historical urbanization, and you know that China has increased a lot in the last decade. With the urbanization has increased a lot, so this has effect on the global warming, on the observed warming. Yes, so the difference in observed warming trend and in cities and their surrounding can partly be attributed to urbanization. So this is for sure with very high confidence. And this impact on urbanization is mainly affecting minimum temperature with very high confidence than maximum, because as I said, this urban effect is more during the night than during the day. And we found also that urbanization has exacerbated change in temperature extreme in cities. So for example, during heat waves or during hot extremes, the fact that you are in a city or outside, it will impact a lot, and it will exacerbate, it will add some more degrees to the heat, to the hot extremes if you are in cities. Yes. Coastal cities also, they are very important, and they are experiencing another important fact is about the sea level rise. So in coastal cities with high confidence, we know that both sea level and air temperature are projected to rise in most coastal settlement. And what is very important is this combination. So if you combine extreme sea level events, you have an extreme sea level event, which is, it can be increased by both sea level and storm surge. So if you combine this with extreme rainfall and river flow, this will increase the probability of flooding in urban area, and this with the high confidence. And we found also that there is a high confidence in an increase in pluvial flood potential in urban area where extreme precipitation is projected to increase, especially at high global warming level. And this is, yeah, more or less the same event that happened here in Wallonia and also in China this summer. So this kind of, so I am not saying that this is due to climate change, but this type of extremes, we are expecting this to be to increase under global climate change. What about air pollution now? So in a warmer climate, so a warmer climate is expected to increase surface ozone by a few parts per million over polluted regions. So I mean here, for example, cities, depending on ozone precursor level, and this is from medium to high confidence. And climate-driven change to meteorological conditions generally favor extreme air pollution episode in heavily polluted environment taught with strong regional and metric dependence, which meaning that we have this climate penalty for surface ozone. And here I am putting a map of the change of ozone at different global warming levels. So top is To the left is at 1 degree global warming, 1.5, 2, and 2.5. And you see here some hotspot here over India and also over China here that that under global warming, we will have an impact on the surface ozone over this region. Yes, so what we need, rapid decarbonization strategy lead to air quality improvement, but are not sufficient to achieve in the near term air quality guidance set for fine particulate matter, for example, by the WHO in many polluted regions. So what we need, I put it here in bold here, the only strategies integrating climate, air quality, and development goal are found to effectively achieve multiple benefits. So we need to have strategies that integrate both aspects, so climate and air quality, if we would like to have an effect in the near term. Yes, so what we need, what we found also for cities, so we found that future urbanization will amplify as it was in the past. So more future urbanization will amplify the projected air temperature in cities regardless of the background climate. And as we found, this signal will be more important for minimum temperature, so more during the night than during the day. So what we know that now is large implications are expected from a combination of future urban development and more frequent occurrence of extreme events such as heat waves, flooding. And so this is with very high confidence that this combination, we will have large implication of this. And of course, if one would like to have the to assess the impact on city, we need impact assessment and adaptation plan in cities required. So we need high spatial resolution because we need the decision maker need spatial resolution that is what we call the decision scale. So if we look to global climate model, maybe we don't have all the information. We need to combine global model, regional climate model, impact model, and taking also into account the uncertainty related to projection. So we need ensemble of projection in order to have an estimate of the uncertainty and also the local impact model. And so we need to integrate all this evidence in order to have a full picture. So this is what we just put here in this map, is that we need we need to combine different evidence, historical observation, climate simulation from global, regional. We need to understand the climate process, and also we need to do some, for example, storyline of complex and high impact events. So we need also, especially for urban area, we need to take into account why how the high impact event can impact the cities. And then we introduced this in this report, but it has been introduced in the past, this distillation. We need to distill all this information together with the stakeholders. So we need to involve them from the beginning of the process, and we do this kind of distillation of information together with them. Just to finish, so this is what that's from the latest report. So the impact, so the cumulative CO2 emission with respect to the warming, so it's more or less linear function. So the more we add to the carbon, so it was nearly linear relationship with the warming. So, and to finish, this is what we know now, is that so here in blue, this is the historical emission, let's say, and so we wanted to know if we would like to limit the warming to 1.5 or to 2 degrees, how much of CO2 we can still emit. So you can see here, we put here the number. So it's 400 gigaton of CO2. If we would like to limit to 1.5, 2 degrees, we have 1,150 gigaton. But what I must say is that in fact, we are emitting every year more or less 40 gigaton. So it will be a matter of decade, and then we can reach this amount of carbon emission. So, and yes, so that's it. I finished with this. If you would like to have more information, you can look to the IPCC website. Thank you very much.
Thank you very much, Dr. Hafiz Hamidi. Thank you for this very insight talk about the IPCC latest report and also urban climate change. This is really challenging to give such a detailed talk in 20 minutes. Thanks again. So our next speaker is Dr. Margit Appeter. She is a project manager of a FP7 Solid project and also co-project manager of Swiss contribution to the Lucy instrument onboard ESA Lagrangian mission and the Clara instruments scientist. She will talk a little bit about how we can track in the energy imbalance from space. Now the floor is yours, Margit. Thank you.
Yes, thank you, Ping. Thank you for the kind invitation to present work we are doing here at PMOD. And now let me quickly share the screen, of course. Let's see if this is coming up well.
Yes.
I have to, okay, can you see the main slide?
Yes, I can see.
Yes, thank you very much. So
Thank you.
yes, thanks a lot for the previous speakers. Indeed, I mean, this is opening the floor maybe for more observations. So my talk will be more towards the observational possibilities to determine the Earth energy imbalance. So the title of the talk is towards determining the Earth energy imbalance from space, the current status and challenges. And of course, this is an observation with which we hopefully will understand the status of the Earth's climate better. And I would like to acknowledge the collaboration. So we collaborate with the Zoom Institute in China with Du Wu, and also, of course, my colleagues at PMOD and with Ping, and as well as the EC international team towards determining the Earth's energy imbalance from space. Okay, just a brief overview. So I will talk about the Earth radiation budget and its imbalance, and talk more in detail about the two components of the Earth radiation budget. Then I will introduce some instrumentation which has been already used to measure these two components. And then I will go into more detail about Clara measurements with which we determine the Earth, well, both components of the Earth radiation budget, and summarize my findings. Okay, so this is the the plot to illustrate the Earth radiation budget. And just as a side note, at PMOD, we are involved in measuring basically all components of this radiation budget. And I mean, just to walk you through this plot, so we have the incoming radiation. That's the direct top of the atmosphere solar incoming radiation. And here the number is, I mean, it's at the irradiance is 1,360 on average, but here it's averaged over the terrestrial full surface. And then this incoming radiation goes various ways. It reaches the ground. It is reflected by the clouds. It's also reflected from the ground, from the surface. But it obviously also is absorbed and heats the terrestrial surface, and this then leads to an infrared radiation that is re-emitted. But this infrared radiation does not always reach space directly. It is, and this is most important for climate change, absorbed by the greenhouse gases and so water and the greenhouse gases. Well, some is directly re-emitted through space, and if we have, for example, a clear sky, this component is larger, which leads to a cooling. But if we have clouds, then the re-emission to space is less. And then we have other processes that the latent heat, for example, I mean, which involve, which give additional components to that. Now, and what, with the climate change, what is very important is we might have, if things are all if things are going well, or if the state of the Earth is, in the ideal case, we have a balance. So the incoming, the amount of incoming radiation is the same as the outgoing radiation. But due to climate change, it has been shown that there's an imbalance, and the numbers change, but they are roughly of the order of 0.6 watts with different values of uncertainties by different authors. And this is the quantity that drives climate change. And of course, I mean, it is due to the human activity and the greenhouse gases. And I would like to say a few more words about this. Let's see if my, okay. And by the way, can you, maybe I should change. So now what is the Earth energy imbalance? And this in a bit more schematic way. So we have the absorbed solar radiation here illustrated in pink, and the instantaneous outgoing long wave flux at the top of the atmosphere. And for the pre-industrial times, this was in balance. So this means the EEI is 0, and we have no temperature change on Earth. However, if we have less outgoing radiation at the top of the atmosphere, this means that we have a positive Earth energy imbalance and a rising temperature. And this is also here schematically shown on this plot. So it is the Earth energy imbalance is just the net value between the incoming and outgoing radiation. And so climate is largely determined by the radiation budget at the top of the atmosphere, which regulates the overall energy content of the Earth system. So this is the atmosphere, land, and ocean. And to determine this value indeed would give a really clear picture, a quantitative picture where we are with respect to climate change. And I would like to illustrate this somewhat further. This is a paper from a figure from the paper by Carina von Schuckmann from 2016 in Nature Climate Change. And here it's again illustrated. So if we have less radiation leaving the top of the atmosphere with respect to the incoming, and yeah, I have to say, so the incoming, of course, includes, well, the total radiation is the direct radiation, which also has a contribution of in the infrared, and the outgoing is the reflected plus the emitted infrared. So it's the balance over the full spectrum. But nevertheless, if overall, if this contribution is less than the incoming, we have a well, this reflects the current status. And what we need to understand is where does the energy go? So, and some of this energy goes into the melting the ice, then a lot, the vast majority of the energy goes into the ocean, and this is 93%. And then we have also a contribution that goes to the land and the atmosphere. And in the bottom panel here, we see, and the talks before have already discussed this a lot, and this is just another illustration of the impact of this difference in incoming versus outgoing energy. So if the energy is trapped in the Earth system, we have an overall an increase of global surface temperature. Then the atmospheric moisture increases. Well, this is due to the atmospheric temperature increase. The land ice decreases, ocean heat content increases, sea ice decreases, the ocean mass increases. So we have a sea level rise. And then we have many more effects. So the extreme, so that this is evaporation, precipitation, extreme events, they increase, as we have already heard. Flooding increases, the number of droughts increases, and snow cover and glaciers decrease. And of course, this is, yeah, this is something that needs to be monitored and also, of course, mitigated as much as possible. And again, if we are able to quantify this value of EEI, we are also in a much better state to determine the future change of climate, because it's a kind of a, I mean, the Earth energy imbalance, because the ocean takes up so much heat. It is also the release of energy has somewhat a delay, and it is also a picture. It is a picture of the future climate change. Okay, and now another figure why it is important to not only measure the surface temperature, but indeed determine the Earth energy imbalance. And there are basically two ways. So first, let's look at the surface temperature change here versus the system energy change. And what we see here, the surface temperature change is not a perfect measure to determine the Earth and system energy, because we have a lot of internal variability in the system. And here the correlation is there, but it is not a perfect correlation. While, for example, if we look at the ocean heat storage, which has been ongoing for really a long time already, this gives a much better correlation. So we can derive a much better picture of how much energy is stored in the Earth system. Nevertheless, we have to understand that the ocean heat, determining the ocean heat storage has also limitation, because we can only measure the ocean heat content through in situ measurements, which have a limited spatial resolution. And now what has been done by Norman Loeb recently, so he put out a paper where he looked at CERES data, and I will come to the CERES instrument in a little bit. So this is just reflecting our knowledge where we are at the moment with respect to the Earth energy imbalance determination. So this figure shows the net top of the atmosphere radiation as measured with CERES in red, and the planetary heat uptake based on the in situ measurements in blue. And what we can see from this is that both show a trend, and the trend is given here. It's 0.5 watts per square meter with some uncertainty, but it's definitely positive. So this means we and this is for the time, I should say, it is from 2005 to 2020. So this is over the full time frame. And both data sets actually agree very well, and they have a robust correlation. So this means that from the net top of the atmosphere radiation, it is possible to track the change in the Earth energy imbalance. However, it is very important to note that the CERES data set is actually linked, so it's not. It needs to be calibrated against in situ measurements, and this calibration, needs to be confirmed independently through other means, in my view. So the absolute scale of the EEI needs to be independently confirmed or determined or confirmed. But overall, this is really striking that we have a positive trend here in the net total radiation or planetary heat uptake. This is very important. Okay, and this is yet another figure by another paper by Carina von Schuckmann. It illustrates again where the energy goes of this absorbed energy for the different time frames. So in bold here are the values from 1971 to 2018. So in this time frame, we are in her analysis of the order of 0.47 plus minus 0.1 watts per square meter. But for the for a longer time, no, for the more recent times, so from 2010 to 2018, we are at 0.87 plus minus 0.1 watts per square meter. So this illustrates that for recent times, the Earth energy imbalance is increasing, and this is also extremely striking. And in her paper, she recommends that the required CO2 reduction needs to be of the order of minus 57 ppm to achieve a kind of a balance again. So to come from the imbalance to a balance. Okay, and here just for completeness, so well, the work here, the work on the Earth energy imbalance is a lot based on in situ measurements, but as I already mentioned, we have the challenge that the ocean heat content is determined from single point measurements mostly over the ocean, which has some limitation, of course, and also it's only the upper ocean mostly that is monitored, and the deep ocean is a challenge for this for the Argo network to measure the deep ocean. But there is also activity that this is actually happening. Okay, so now I would like to come to the measurements of the top of the atmosphere measurements and the two components of the Earth energy imbalance. And I have to check maybe the time. I'm still have some time left. So I would like to illustrate where we are with our understanding of the total solar irradiance and also the Earth outgoing measurements. So what you can see here is a figure showing in gray here the most recent measurements from it's the PMOD composite in gray, showing the top of the atmosphere TSI measurements by all the TSI instruments that are available, and the reconstructions for the past. And of course, if we want to understand the climate system, we need to know the present, but with high precision, but also the past. Nevertheless, we can see that even though we have precise measurements, there are also uncertainties that need to be assigned to it. And currently we are, and this is not on the figure, but we are at a precision of about 40 ppm per year. But this is well, this is the status of the possibility of the TSI measurements. And what we have recently done at PMOD, we have put together a new Virgo data set. So Virgo is the instrument on the SOHO satellite that is now measuring for more than 20 years, 25 years now. And we have a new data set available that can be used for these kinds of studies. Okay, and now if we talk about the two components of the Earth energy imbalance, what is very important is to keep in mind, typically TSI is shown as the normalized value at 1 astronomical unit, yes, which is the red curve. And in this figure, it almost, well, it can be seen as almost constant. Now, what is absorbed at Earth is, however, the black curve. So, I mean, the variation here is the annual variation due to the eccentricity of the Earth orbit around the sun. And now we have to really understand if we want to determine the Earth energy imbalance, we also have to consider that we are looking for a signal of 0.1 watts per square meter within this enormous variation. So what I want to say is that the natural variability of the TSI is already very high, and and therefore we need to look at long-term means in order to be able to determine the Earth energy imbalance, and in particular its trend. So it is a challenging measurement we are after. This is what this figure should illustrate. Okay, now let me come to the instrumentation, and this is not this should not be a complete picture of all instruments, but I want to illustrate basically two different methods how we are measuring the Earth outgoing radiation. And a key instrument is the CERES instrument. This is a NASA instrument, and the PI is Norman Loeb, and this is a scanning instrument. So with this instrument, we are, the team is able to measure the Earth outgoing radiation by varying the angle and scanning for all possible angles in order to understand all contribution, so all angular contributions of the Earth outgoing radiation. Now here, this instrument is not, it is calibrated, but it is not on the absolute scale. It cannot produce values that are on the absolute scale. And therefore, as I mentioned earlier, the CERES team needs to cross-calibrate their measurements to an independent data set. On the other hand, we have non-scanning instruments. So here, and there are two sets of instruments. We have the wide field of view instrument, which is, for example, the SIMBA instrument in Belgium, and maybe we also have authors or collaborators of the SIMBA team online. And of course, you are invited to comment on later in the discussion. And there's the Raven instrument by JPL from Bill Schwartz. And these instruments measure the Earth in a wide field of view, so they have the full Earth from horizon to horizon in their field of view. And on the other hand, we have a narrow field of view instrument, which is the Clara instrument on NORSAT 1 that has been built by PMOD. And probably the key difference to all of the others is that Clara is SI traceable, so it is really traceable to the absolute scale of watts per square meter. And I would like to say a few words about NORSAT 1. So this is a Norwegian low-cost satellite. It has 3 payloads, an automated identification sensor for ship tracking in the Norwegian Sea, then Langmuir probes and the Clara TSI radiometer. It has been launched in 2017, and it has a polar low Earth orbit with a midnight noon local time, and it is at a height of about 600 kilometers. And this is how it looks like. This is just an illustration of the payload, and here we have the front side, so the sun, the side of the side of the satellite that is pointing to the sun, and with the solar panels, and here we have the Clara radiometer, and this is a real picture when it has been on the shaker in Canada. Okay, here just for completeness, a few other images. And I think I don't have too much time. Now, what is maybe to illustrate how the Clara instrument works, and maybe this is a bit more detailed, but I just want to highlight that we have a precision aperture in the front and the viewing limiting aperture in the back. So we have a narrow field of view, and this is needed for the solar measurements and also for the And at the same time, as in our view, it has advantages for measuring the Earth outgoing radiation. Okay, and here are just some details on the first light measurements of the 3 cavities. So I haven't maybe shown you this in detail, but we have 3 cavities on board to track also degradation of the measurements. And we have well, different precision of the different cavities, but overall we can confirm the TSI of 1,360 watts per square meter, but two of the cavities are actually somewhat, so the cavity 3 shows a higher reading and cavity A somewhat a lower reading, but overall the absolute scale is within the uncertainty. Okay, and this is the TSI measurements that we get from Clara since late 2019 to now mid 2020. And well, the data, they still show somewhat a large scatter, but overall we can follow actually solar activity to some degree, where we need to do some further studies as to what causes this scatter. But overall, we can confirm that with Clara we can actually measure TSI nicely. And now this is maybe a key plot of my talk, and what I would like to highlight is that with the Clara instrument, we are now able to measure the total solar irradiance and the Earth outgoing radiation. And don't focus on the numbers. These are really raw data as they come out of the instrument, but it illustrates that for one day, we take solar measurements, and when the satellite goes into eclipse, so it goes behind the sun, behind the Earth, apologies, then we measure the Earth outgoing radiation, and then again, the solar measurements, the Earth outgoing radiation. And with these measurements, we really have for the first time SI traceable TSI and Earth outgoing radiation measurements observed with one instrument. Now, of course, instruments are not perfect, and the satellite is not perfect, so we do still face some challenges. So this curve actually shows now a zoom in into these times. And what we see is there's still a lot of variability. And as a matter of fact, I mean, these plots are preliminary, but well, first of all, it shows that the instrument or the measurement concept is realistic, but we still need to do further data filtering in order to be able to have robust values, because due to the satellite motion, there are also solar measurements in between. So this is not yet clean data, but what I want to show is that SI traceable measurements measuring TSI and Earth outgoing radiation is possible. And here I'm showing the long time series now from early 2020 to August 2021. And again, the variability is, please don't take this is really preliminary, but we are working on a refined data set, and we hope to be able to give a product soon that is, well, that contains SI traceable outgoing long wave radiation measurements from space. And from with that, we will hopefully be able to at least measure the outgoing long wave radiation or determine the outgoing long wave radiation from Earth for the first time with an SI traceable instrument. Okay, and with this, I would like to conclude with a slide indicating the challenges to measure EEI. So first of all, we have an imperative to measure EEI from space in order to determine the climate change status of Earth. So where is the Earth with respect to its imbalance? And then the measurements of the heat uptake from in situ measurements have limitations, because these are single point measurements, and even if we have values of Earth energy imbalance from the in situ measurements, there should be an independent confirmation of this value from space. And simultaneous measurements of incoming TSI and terrestrial outgoing radiation is, in our view, an ideal setup, because I haven't talked about this in detail, but it reduces the uncertainty on of the overall determination of EEI, because if we do it with one instrument, it reduces the uncertainty. And then, while scanning the terrestrial surface with a scanning instrument has limitations, because while this instrument is not calibrated to an absolute scale, at the same time, wide and narrow field of view instruments also have pros and cons. I didn't go into too much detail, but for example, a wide field of view instrument, well, it sees the horizon of the Earth. Yeah, it doesn't see the full Earth, but from horizon to horizon, and it's also difficult then to judge where exactly the radiation comes from. And so our preference is the narrow field of view, because with this instrument we can determine better where the radiation from Earth is coming from. So in summary, there is a lot of technical challenges still to overcome, but at the same time, we are on a good track to determine the EEI from space, hopefully in the near future. Thank you very much, and I'm happy to take questions later.
Yeah, thank you, Maggie, for this very informative talk on the Earth energy imbalance. I'm sure we will discuss later. Yeah, so now we go to the next talk. It's given by Dr. Ziming Li. He's a senior research fellow FRS from University Catholic Leuven, and he's an expert on soil, plant, and climate relationship. So Ziming, you have the floor.
Okay.
Share screen.
I have to unshare.
Yeah, you need to click unshare the
screen. Just a second. It's disappeared. It's
at the bottom.
It's funny, there's no
stop sharing.
Mm-hmm.
You can do it.
Can you do it for me? Maybe I should go out of.
Okay, I stopped it.
Yeah, that's fine. Yeah, thank you.
Ziming, try yours.
Okay, hello. I'm trying to share my screen. Okay. And it's a bit strange. Okay, I think it's here. Share.
Sorry, Margaret, we are still seeing your screen.
Yeah, we are.
Yes.
Sorry,
it's on the
you
top.
Know what? I just closed my. Now it's.
Yeah. It's. Could you please speak again?
Desk.
Stop sharing.
It's a bit strange. Okay. Close or sorry. Apply, share. You see that I cannot open the desk one to share my file.
Yes, to me, I think you should first open your presentation, then you click share.
Yes, yes, I opened my presentation already.
Then you can select which contents you are going to share. Yes, we see your folders, I think.
You see that?
Yes, we see that. It's your folders.
I'm trying to open, but
maybe if you unshare and then open it again, try to open it.
一般你的 PPT 点放映就可以了。
是吗？
啊，你刚才桌面已经分享了 ，PPT 点
好的
放映就
好的
可以了。
那行。Okay. Sorry, I give. It's okay now. Can you see that?
Not yet.
No.
No.
还没有 Not yet.
好奇怪，我上一次都成功，但这次不知道为什么。
你刚才分享的是桌面，你把 PPT 分享就可以了。
这样能看到吗？
没有，你现在还没开始分享。
很抱歉呢 ，Sorry。
没事，不着急。
现在可以了吗？
还是没有。
奇怪。
Maybe you have to confirm that you share your application.
Yes, yeah. I put my slide on the desk and to wait to share, but here it doesn't work. No reaction. It's a bit strange. But now I'm trying to close and reopen again. Ah, yes. I think something happened here. Ah, yes, I think it's coming. Now you see that? Okay, I tried.
Do not see.
Perhaps you can try to share the whole screen, then.
No, it's yes. Yes, I think now it's okay, no?
No, we do not see.
Now it's okay?
No.
你好像没开始分享吧？
我已经分享了，而且打开了，你知道吗？而且点开那个了。我发给你吧，殷老师，要吗？
你发给我，
但是太奇怪了，今天。
Okay, you send to me.
我微信发给你了啊。我这里点开是可以的，但是不知道为什么打不开。
I will try to share the screen. Okay. Do you see?
Yes.
Yes.
Oh,
It's okay
okay
now. Yeah.
Okay. You can start. If you need, I click. Tell me.
好的，行吧，那就全屏吧。You can have.
I think it's full screen now.
Okay. I'm so sorry for this problem delay hour the meeting. I don't know what happened today for my computer, so I'm so sorry for this. And hello everyone. Good morning to my friends from Belgium, and also to good afternoon to my friends from China. First of all, I would like to thank for the invitation from Professor Ying and Professor Zhu to join this meeting. It's my great honor to be here for this talk. My name is Ziming Li, who works in the UCL Leuven with the founder of FIS. Before this talk, I would like to give a brief introduction regarding the role of silicon around our daily life. Okay, now we can go to the next slide. Okay, from this picture, I think we can see an interesting story regarding the role of silicon affecting our food. This is a nice story, so I want to share with you, but I don't know why. Does it show like this? Because I'm not animal scientist. Because my major focus on the soil and the plant system. So now we can see our soil and the plants with an effect of silicon. Next slide. Okay, this picture, it's give us a clean information to see that if we give a high silicon application, we can get a higher rice biomass compared that without silicon application. This is very important. Let us to know that silicon can affect our crop growth, even though without any stresses. Next slide. Indeed, silicon is not an essential element to the plants, but lots of reports have shown that the silicon can be involved in many plant function group during their growth, especially that silicon has a beneficial effect with the climate change. From the next slide, we can clearly see that with the climate and the environment change, like the CO2 increase and heat stresses, and also drought stresses, and other biotic stresses with heavy metal pollution, it largely affect our crops and also the plants. But if we can apply the silicon in our cropland with these stresses induced from the climate change, we can get the positive response to increase our crop growth. Next slide, we can clearly see that once the silicon uptake by the roots, and it can transport in the plant tissue, where it can happen the precipitation to form the phytolase. This phytolase is like the plant, the bone, like the planted bone against lots of abiotic and biotic stresses. In fact, during the plant growth, some phytolase can occlude some organic matter. Normally, this ratio is 1 to the 6%. From next slide, I can show you that some organic matter how can be oh, sorry, so fast. From this picture, and we can see that during the phytolase formation, it can still also occlude some organic matter. From the right of the picture, you can see the dark zone, which is some organic matter occluded in the fatulase. Because this picture is very nice, we pick up one the fatulase and we cut a very thin section, and to see that where it's occluded carbon in the fatulase. This occluded carbon in the fatulase can be returned in the soil and affect the soil organic carbon sequestration. From next slide, I can share with you to see that how it's fatulase occluded carbon to affect the sequestration of soil organic carbon. From the first graph, you can see that over the time, fatulase occluded carbon can slowly happen the decomposition, but the total soil the carbon can quickly decompose over the 2,500 years. And we can see that fatulase occluded carbon contribute 18% of total the carbon in the soil. It means that over the time, this carbon occluded by the fatulase can be stable in the soil and give a long carbon sequestration. This is why that I want to study the fatulase occluded carbon. From the next slide, we can see that this topic only starts 20,000 years ago. After 2,000 years, the study regarding of fatulase occluded carbon quickly increased. In this year, you can see that there are 35 papers published in the journal talking this topic, but this study mainly focus on the lots of soil and plant system regarding its estimation in the soil. But from next slide, now we can see that okay, okay. Okay, we can see it's okay, no problem. The past study only focused on the fatulase occluded carbon estimation, but how it's a biological silicating processes affect the carbon sequestration in the fatulase. So to better understand this effect, I carry out three objectives to understand how the silicon fertilizer to affect the carbon sequestration in the rice ecosystem. The first objective, and we focus on the field rice ecosystem. We extract the fatulase from the rice crops, and we found that the fatulase also can occlude some organic carbon. It's one the fatulase, you can see that can occlude 6% of organic carbon. And finally, we choose 5 next slide. and we choose 5 typical the rice cultivar from China, Zhejiang, Xitan. The right graph clearly shows that the rice cultivation largely affect the fatulase occluded carbon sequestration, and you can see that only the Xianghu rice can give the bigger contribution on the CO2, the sequestration within the fatulase. This graph means that if we can optimize the cultivation of the rice, we can estimate the position of above ground fatulase occluded carbon sequestration in the rice ecosystem. It means if you want to increase sequestration of fatulase occluded carbon in the rice, you must choose the best ability to occlude more the carbon. But this means that we don't any the option to keep the best quality for the rice the yields, because this is not practical in our world. It means that we have lots of different rice plants, and also we have to keep our food yield. So it means that the best way is to find another solution to increase the potential of fatulase occluded carbon in a rice ecosystem. So the next objective, and I choose silicon fertilizer, the basalt powder, to amend the rice the crops, to check how the silicon fertilizer responds the sequestration of fatulase occluded carbon in the rice. From the left of the graph, we can see that if we increase the application of basalt silicon fertilizer, we can quickly increase the fatulase the content, and also increase the content of fatulase occluded carbon in the rice the plants. It means that this is a positive response to increase the sequestration of fatulase occluded carbon in the plant tissue. On the next slide, and we can see that the potential of fatulase occluded carbon in the different organ fatulase is also totally different. But anyway, if you give the silicon fertilizer in the rice crops, it means you can increase the potential of the fatulase occluded carbon in the crop land. But another thing that from the objective 2, because the basalt powder can also contain some heavy metals, it will affect the rice the crops, and finally the food yield with the climate change like heavy metals. So that finally I choose another common silicon fertilizer to carry out my objective 3. So from the next slide, I can share you about the common fertilization of silicon and phosphorus, which is widely used in the rice cropland, because this is very practical for the farmers and also for us to get enough the rice the yield using the common silicon and the phosphorus fertilizer. And the major point that we want to use this point to test the response of silicon and phosphorus fertilization how to affect the sequestration of fatally occluded carbon in the rice ecosystem. From the graph 7, we can see that if we increase the both fertilizer of silicon and phosphorus, it's true we can quickly increase the potential of fatally occluded carbon in the rice, but over increase the fertilizer, the application, it show a decrease. It means that it doesn't show a direct response with increasing both fertilization of silicon and the phosphorus. So in our future the cropland, if you want to improve the potential of the carbon sequestration in the fatalities, it means that we have to find the best solution to optimize the silicon and the phosphorus fertilization to respond to the sequestration of carbon in the fatalities. Okay, the last point I can give my conclusion that fertilization increase the carbon sequestration in the fatalities can be which can be positively response to the biogeochemical sequestration of atmosphere CO2, because during the plant growth, this organic matter is from the CO2, but this in fact largely results from the increase the fatalities concentration and also the rest biomass with increasing fertilization, even though that phosphorus. But this topic is still very limited understanding other the parts in the future. The cropland like the wheat and the maize and banana and bamboo. So if we want to improve the sequestration of carbon in the fatalities, in the future topic, we should calculate the cost, referring each the practice like a fertilizer and something, and also that to choose the best crops to increase the carbon sequestration in the fatalities. And also we have to better to quantify the different measures, how to more effectively increase the carbon sequestration in the fatalities. The important thing that we have to understand the molecule, the magnesium, how to regulate the carbon sequestration in the fatalities, because this part still is not totally clearly, because from our study, and we found that when we apply the fertilization, this any of silicon the fertilization and does not give any the response on the concentration of carbon occluded in the fatalities. It means that we should understand the molecule, the magnesium, how to regulate the carbon sequestration in the fatalities during the plant growth. Okay, thank you for your listening. This is my
thank
topic.
you, me.
Yes. Okay,
yes,
I finished my topic.
Interesting talk. So now we will go to the next speaker because we are tight in time.
Yes, I'm sorry for this problem.
No, it's not your problem. Yeah. Thank you.
Our next.
Desmond.
Yeah, thanks again. It's me. Our next speaker is Osku Gaiteki. He's from Royal Observatory of Belgium. He takes active part in several space missions, for instance, ExoMars and DART InSight from NASA and MMX from JAXA. He's a leading scientist of the grasp gravitometry and UETAS CubeSat for ESA's HERA mission. Now let's give the floor to Oskus. He will talk about the Earth UV. Thank you.
Thank you, Ping. Can you see the main screen?
Yes, also the small animations. Yes, we see.
Yes, okay. Okay, I will take you, I think in this talk, a small trip in the solar systems, leaving the vicinity of the Earth. But there will be also some references to the climate, because we'll talk in general the asteroids is a threat and opportunity for us. So the asteroids, they are the remnants of the collisional past of the solar system. So since the early phases with the collision accretions of the planetesimals, the planets and the large objects were formed, and the giant impacts shaped the present solar system that as we know today. The collisional process continued actually till the late phase, as we can see still on some of the asteroids. And traces, almost all solar body or solar system objects are visible, starting from the moon, which is covered with many craters, as you know, going to Mercury or Mars. We have really large basins, thousands of kilometers large. And we can see the impact traces on icy moons like Europa, or on the comets, on Pluto, even on Kuiper belt objects, like the one that I don't know if you can see my mouse, but on this body that's recently discovered, it's called Ultima Thule, and this was a surprising, discovery, because they're very low speed due to their distance from the Earth, those objects, and we were not expecting to see any strong or energetic impacts there, but we can see large craters there. So they are everywhere. Of course, these are the remnants of the past, but we still see them. And one of the maybe the good places to look is Mars, where we, thanks to the continuous, many orbiters around Mars, we were able to see more than 1,000 new impacts over the last 2 decades. These are usually small impacts. As you can see on the right-hand side, it's only meters, order of meters. And those impacts actually, they take out the material from the surface, and we can see the bright subsurface material, which indicates, of course, the water, icy water. And looking at the spectrometers, especially at the center peak of larger craters, we can see also the alterations, signs of alterations of minerals by the long-term presence of water, which of course suggests the hydrothermal activity due to the impact processes. So these are all important, especially for the early Mars, this large impacts and presence of water, because this is one of the main questions related to the habitability of Mars, maybe 4 million years or 3 million years ago. We have also a new lander, it's called InSight. Observatory is involved with that. It's to study the interior structure. Of course, he's looking also to observe those impacts. But if we know the exact position, this is a single seismometer, if we know the exact position and the mass of this impact, then we can reduce maybe some constraints about the subsurface. That's what is done. This is a paper that came, I think, last week with my colleagues in the InSight team. That's what's exactly done, but using the Perseverance, the Mars 2020 lander ballast. These are almost 80 kilo titanium objects that were released before the entry. We know their weight, we know their trajectory, and this is image of the crater that caused it's 6 meter almost diameter, and then we can use that one to calculate the dissipation factor or the K of the crust and into subsurface material. We didn't get the signal there, but nevertheless it's a good, because that allows us to take out some of the parameter range and constrain our knowledge of the crust or subsurface material. Of course, so we can do something similar for the atmosphere, the signal in the atmosphere, These are objects that comes really at high speeds over the sound of speed, and they create infrasounds like on the Earth. It can be man-made or natural objects, and we can study the acoustic sources and their damping, and we have a very good pressure sensors, and we did that, for example, for the Tianwen-1, the Mars entry probe, and this study is still, continuing there, the analysis of the data. As I said, the early impacts could have caused or affected the climate on early Mars. That's an interesting topic, and we look at that with some colleagues also with in different groups there doing that. We are not the only one, of course, to study that. And this study, for example, here that I refer shows what could be the consequences of a large impact on Mars, early Mars. Was it be able to sustain enough, warm climates so that we can see any change like long-term water there? So that allow, this simulation shows, for example, after 10 years, the temperature changes, and then the accumulated rainfall. And another topic that's really interesting also to see if we can, due to these impacts, release some of the gas from the subsurface. We know, that we have really large impacts early in the Mars history. And we know also that the subsurface is rich probably in ice, also methane, that could have caused at least temporarily warm and wet conditions on early Mars. This is an ongoing topic and research on Mars. Of course, when we come to Earth back, we see also some very beautiful craters. That is the Barringer or meteor crater on Arizona. It's about 1 kilometer diameter. This occurred 50,000 years ago, and we know, how devastating for life could it be a big impact from the famous Chicxulub impact crater that happened in the CP boundary 65 million years ago. And there has been a lot of studies. These are just some of the example of the large literature of this, the effect of this this impact cratering event. There is like studies that looks on the possible the climate models just discuss how change and how long this change stayed due to this impact. Of course, one of the main question is the aerosols in the air. Can they block the sunlight? Is it usually it's cold after such an event, like a nuclear winter? But then this requires actually better understanding of the dust particles or aerosols in the air. And thanks to recent expeditions, they were able to get out new material that also shows that the long-term resisting hydrothermal activity. This is also important for habitability on Earth or Mars, but also shows the mass of the ejecta in the atmosphere. We were able to get better models about the dust, how long it stays. So this is a very recent study from my colleague Jem at the observatory with our colleagues from VUB, taking into account the dust information that comes from this expedition new data. We were running some of the simulations. This shows, for example, the effect of the dust just before the impact. This is really after the impact, the global daily mean temperatures. This is after a year, and this is longer time scales. And this is done for the different effects of dust, sulfur, or soot following this impact. And this is an ongoing study, but I think you can find the GSA presentation online there if you're interested in this topic, of course. And so Chicxulub is the most important, most well-known impact structure on the Earth. But we have many others. We have almost 109 confirmed impact craters, and probably when they occur, they cause maybe not all of them global effects on the climate and habitability, but some of them cause also the local or regional scale damage. And what is interesting to see is that younger structures dominate. This is of course normal because the older ones or the big ones, they disappeared from the surface. And this shows the number of craters as a function of time. and the older ones, of course, they get eroded, and the young ones they stay here. So we have many craters between 0 and 10 kilometers. Actually, not all of the craters also, I mean, meteorites or the bolides, they reach to the surface. We know that some of them, this is, they come and they cause an air blast. So this is a fireball, Chelyabinsk meteor air blast, recorded by a Russian driver's dashcam. This created actually an energy in the atmosphere almost an order of magnitude larger than that of Hiroshima bomb. So you see the effect on the video there on the top. And we have seen many of those in the past 40 years. Many of those large ballasts in the air that created each time big energies, and this can cause also a lot of damage. Most of them they occur in places, remote places, but in a city center or in large populated areas that can cause significant damage, of course. So this is an infogram showing, actually summarizes that. So we have small ones that come very often, every 2 weeks, and it's like continuously bombarded. Some of them, the big ones comes, like the one that I just showed in the previous slides. This occurs almost every 10 years. And then the big ones, really that Chicxulub, etc., they comes in a million-year scales. And the energy that cause the small ones, yeah, it could be maybe kiloton level, Hiroshima bomb. The larger goes, of course, the energy increases, and this was the Chicxulub estimated to be 100 million megaton TNT equivalent energy. What is also interesting is that we know, I mean, most of the big ones, so they are not really the biggest threats. I mean, we know their trajectories, etc. We know that they exist, their trajectories. What is difficult is to find the ones that lower than 100 meters. And these are still can cause either a very strong air blast or can reach to the surface, of course, this is 100 meters. But I mean, more than 80% are not known. We estimate, only estimate their numbers. And as this plot shows, we know the big ones, but if we go to the smaller ones, less than 100 meters, yeah, they're still unknown. So it's likely the trade, there's a trade coming to be those ones, the small ones that will cause in the let's say in the future. Those asteroids, you know, they're mostly between Mars and Jupiter, but also orbit with the larger planets, Trojans on the Jupiter. We have also Trojans on Mars. But there are also many close to the Earth. These are called near Earth asteroids. We have more than 23,000 of those. And some of them, which are coming very close, less than 20 lunar Earth distance, they are called potential hazardous asteroids. These are more than 1,000. And they're difficult to find because, as you see, they come from a high inclination. So difficult to find. Only in the last minutes we see that. For example, this happened in 2018. The trajectory of an asteroid is about a kilometer diameter, come very close to the Earth. So the question based on the past of the Earth is if there will be a next impact, but rather than when the next impact will occur. So that's what motivated ESA and other space agencies to put in place planetary defense systems, which is basically observations to detect those threats, to assess them, and then to find solutions. And these are mostly the deflections. And one of the good examples is the IDA international collaborations between European Space Agency and NASA. So next month, I think end of November, the DART spacecraft will be sent, and it will be on a trajectory to hit the small moon of the Didymos systems. This is a binary moon system. So the impact will occur next year in October. So it's a very simple experiment, actually. It will go directly and hit. And from the observations from the Earth with radar and telescopes, we'll see the effect of this collision on orbital parameters, mainly the period of the rotation of this secondary or the moon of the Didymos system. Then we will have Hera spacecraft with its CubeSat that will come to the system. It will be launched in 2024. It will arrive several years later on Didymos binary system. It will have the cameras, altimeter, also a thermal imager that made by JAXA, but also there's Belgian contributions there, and the two CubeSats, and will look actually from a distance to characterize the moon, especially the impact structure there, and to better understand the efficiency. I mean, this is needed to really quantify the DART impact, to better understand how the impact the crater is formed, how much energy was given, and etc. And also it will be, I mean, it's not only technology demonstration, but it will also allow us to understand many things about those asteroids. And it's one of the important contributions is going to come also from the CubeSat. So this is a Juventas CubeSat. There are two CubeSats. This is one of the CubeSats, and this is going to help the Hera to reach its research and mitigation assessment objectives. It will complement specifically by providing better understanding of the interior structure, as well as the dynamics and surface properties. It will do that by carrying two main payloads. It's a low frequency monostatic radar called Jura, and a GRASS gravimeter. And gravimeter is made in collaborations, but it's the Royal Observatory of Belgium is leading that GRASS gravimeter. So the main objective of Juventas is to get, of course, the interior structures, combining the radar plus the gravity field measurements, but also it will land on the surface and help to provide information on the surface properties there. So this is the consortium that we have. It's contributions from different countries with different roles of their Royal Observatory of Belgium is, as I said, it's leading the investigation and also develops the gravimeter. We have from France and Germany the team for the radar, and Italy is involved with radio science, etc. So this will be all part of the Hera team, of course, and the data will be shared. And one of the interesting part of the CubeSat also, it will attempt to land. CubeSat will land, but Juventas is equipped specially for that. So it will use its GNC sensors, and we did many simulations for the landing at the velocity, because this is only, I mean, it makes under 60-meter diameter object, so it's also very low gravity. It's a very tiny object, so it's a big challenge to land. And not only land, but you can touch maybe the surface, but to stay on the surface on such a low gravity environment, it's quite challenging. So we do some simulations. So this is coming from my colleague Stefan from GomSpace, looking at the possible landing scenarios, the speeds, and also how we use this data, like accelerometers, to learn about the surface mechanical properties. So then if we manage to land, we'll do the operations with the gravimeter and also other instruments to better understand, of course, the gravity field, the surface accelerations. This includes also the tides, rotation that Vernick will talk later, and then about to combine those measurements with the previous ones of the radar and the gravity from the orbit. So this will actually allow us to understand better not only the interior structure, but also it will contribute the science objective of the Hera, or this deflection technology demonstrations. So these are on the left, you can see the Hera mission objectives, right on the Juventas. The name systems, global properties, but I think the most important from science, it will be to understand their interior structure and compositions. Because this is also important for future, as you know, they're like those asteroids. They are threat because they are because close to the Earth, but also due to their proximity to the Earth, they can be easily accessed and they can be used as a resource, especially for their raw materials. And so if you know better their interior, what they're made of, it's easy, of course, to diminish the risk and of such emissions. But the economic analysis indicates that the cost of returning sustainable materials to Earth should be at least, should not outweigh their market value. This is not the case for the moment. Maybe in future it will change. And then maybe the most interesting part will be to use the volatiles, and H2O is a fuel for future exploration missions. But there are already, some ideas and thinking about how we can use those materials. Although there have been several active asteroid mining companies, it's not presently cost effective to do that, of course. But this doesn't stop, of course, the space agency like NASA to study, to catch some of the rocks and bring to the Earth vicinity. So that's the summary. Maybe just I'll go truly. So this is the asteroids, the remnant debris of the solar system. So understanding their structure, interior, that helps us to understand better the formation process and the history of the solar system. They witness the collision evolution of the solar system, of course, and the impacts on Earth or larger planets. They cause likely the climate also have impact on habitability. That could be both positive and negative with hydrothermal systems or mass extinctions. And on the daily basis, we have hundreds of tons of interplanetary material coming to the Earth. So that's the reason the Space Agency put the planetary defense programs. These are mainly technological demonstrations, but also that allows to better understand those bodies and asteroids. And this understanding also that can help in the future to exploit their raw materials. Thank you very much.
Okay, thank you, Osku, for this very interesting trip to the solar system. Thanks again. So our next speaker is Udo. He's from Changchun Institute of Optics and Fine Mechanics and Physics, and he's visiting PhD student at Royal Observatory of Belgium. His work is mainly focused on the electronic interface design for TSI measurement or source radiation measurement from space. Thank you. Now, floor is yours, Udo.
Hello, everyone. Can you see my slide?
It's coming.
Okay. Oh,
yes,
oops.
Yes.
My Zoom meeting, my Zoom application is something wrong with this application.
We can see your slides.
Okay. Yes. Okay. Okay. Hello, everyone. My name is Duo Wu. I'm from the Solar Radiometry team of Changchun Institute of Optics, Fine Mechanics, and Physics. I'm glad to be here to share you something with the optical and electronic interface designing for space radiometry applications, the relative radiometer. JTSIM, the Joint Total Solar Irradiance Monitor, is a solar and terrestrial radiation measurement experiment. It is composed with the solar irradiance absolute radiometer to monitor the total solar irradiance, and the solar relative radiometer SRR and Earth relative radiometer ERR are introduced, which allows to measure the radiation from the Sun and the Earth at the same time. Here is the data sheet. Oops. Here's the data sheet of the SRR and the ERR. We can see the spectral range, the field of view, the dimension, and the mass.
We don't see your slide. We only see the first one.
Really?
Yes.
Okay, so I'll
yes.
quit and
yes.
I'll quit and coming again. Sorry. Wait a minute.
Yes. And also,
okay.
Yes.
There's
also
something
put
wrong
it in
with my Zoom application. Yeah.
Sorry.
Put it in full screen. During this time, I saw several people has already asked the questions in the chat. So I saw Professor Yu has answered some of them. If any of you have questions, please don't hesitate to put in the chat. Thank you.
Hello, can you see my slide?
Yes, we can see your slides. Can you put it in full screen?
Well, the GTSIM is the solar and terrestrial radiation measurement experiment. It's composed with SEER, the solar irradiance absolute reductor, to monitor the total solar irradiance, and the solar relative reductor SR and the Earth relative reductor ER are introduced, which allows to measure the radiation from the sun and the Earth at the same time. And here's the datasheet of SR and ER. You can see the spectral range, field of view, and dimension and mass. And here's the prototype of two relative reductors and their electronic interface holder. The instrument is ready to fly on a micro satellite or a meteorological satellite, such as Zoom. Zoom is a meteorological satellite operating in a synchronous orbit. It mainly provides the scientific data for weather forecasting, ocean and ice monitoring, climate monitoring, atmospheric chemistry, and space weather research. And the relative reductor is developed from the PICARD mission, which has been operated from 2010 to 14. The scratch shows the working principle of the main detector of the SR and ER. Both of them are coated with the high absorption rate black painting, and the main detector is connected to the heatsink with a shot. The main sensor is mounted on the cases through polyimide pad. We designed the cases with different apertures and introduced the active thermal control unit. And a parabolic reflector is also added for SRR to improve the absorption rate of the sensor. For ER, the apertures can block the sunlight and radiation emitted from the surrounding instrument. Here is the measuring requirements of the relative reductors. First is the power, second is the data rate, the third is the thermal environment. To meet these three basic requirements, we designed the electronic interface. Here is the function of the interface circuit. The first one is to provide the power and clock signal for SRR and ER sensor. The second is to sample the output of SRR and ER. The third one is to communicate with GTSIM. Here's the prototype of the interface system. It mainly contains two PCBs. The first one is to convert the system 28 volt to plus and minus 12 volt, 8 volt, 5, and 3.3 and 2.5 volt. The second one is to sample the output of SR and ER sensor and communicate with GTSIM. Here is the power supply system. We choose 4 space grid chips to do the power convert. The 8 volt is mainly for the sensor's power supply. The 3.3 volt and 2.5 volt is for the FPGA power supply. The plus 5 volt is for the communication system, and plus and minus 12 volt is for the instrumental amplifier and pre-drive converter. And here's the multi-channel acquisition system based on the wave converter. And we have the signal from the sensor box. They first go through the instrumental amplifier, and then it comes to the wave converter. And then we use a D-trigger to sharp the waveforms. And finally, we use FPGA to make a counter to count the output of the wave converter, and we finally get the value of the sensor box. And we also use the FPGA to do to generate the clock signal for the sensor box. Here's the flight model. The flight model of the electronic boxes. The figure below shows the preamp circuit based on the locking amplification technology. First, we use the resistor bridge to do the modulation, and then we use the analog switch to do demodulation. And we use two instrumental amplifiers to do the amplification. Here's the flight model of electronic box, and also the flight model of sensor box of relative reductor. This is ER, and this is the SR. We tested the octa-black and the carbon nanotubes as the black coating of the main detector. We examined their absorption coefficients by using a 632 nanometer laser source. The octa gives 99%, while the carbon nanotubes has a 97.9% absorption rate. From this result, the absorption rate of octa-black is higher than that of carbon nanotubes at the 632 nanometer. To calibrate the relative reductor, we use CR4B absolute reductors, which is traceable to the watt reductory reference, and 30 milliwatts fiber laser source. The shutter frequency of the absolute reductor and relative reductor are both set to 180 seconds. The experiment date is shown in the figure below. The red one is the original record of the relative reductor. The right one shows the temperature differences and the power measured by the relative reductor. Here's the results. The average power is 30.65 milliwatts measured by the absolute reductor with a repeatability of 5.24 10,000. The average power measured by the SRR is about 30.1 milliwatts with a repeatability of 5.27 10,000. And the relative reductor is very sensitive to the ambient thermal environment. In order to evaluate the impact of the thermal environment on the relative reductor's measurement results, a water-cooled platform is used to simulate 11 different ambient temperature conditions. We repeat the radiation power measurement at 14 degree and increase it by 1 degree step to the 23 degree. We show here the power versus temperature distribution. The left one shows the changes of platform temperature, case temperature, T1 and T2 temperature during the test. The right one shows the power response versus ambient temperature of water-cooled platform. And then we do the field compression test between SR and CR2C absolute reductor traceable to the WR. The deviation between the correct measurement results of the SR and the CR2C is about 0.3%, and the correlation coefficient is about 0.996. Test the repeatability of ER measurement by using integrating sphere light source with a 600-second brightness change period, 35 times measurement. The repeatability of ER is about 3.72 thousand. The differences of repeatability result between ER and SR is mainly caused by the large field of view of ER, which will be influenced more easily by the environmental convection. The left shows the original record of the relative radiometer. The right shows the temperature differences and the power measurement result of the relative radiometer. To summary, comparing to the absolute radiometer, the SR reaches the same level of repeatability, about 5.2 10,000. The Acta Black has an absorption coefficient of 99%, while the carbon nanotubes shows a value of 98% at 632 nanometer. And then the field experiment indicates a 0.3% deviation to the WR traceable absolute radiometer. The repeatability of ER is about 3.72 thousand. The 0.3 differences between the SR and the traceable absolute radiometer measurement needed to be further investigated. In general, by introduce the new optical elements, mechanical holders, and the active thermal control unit, the SR and ER has reduced at least one order of measurement uncertainties than the Picard balls. Okay, that's all my presentations. Thank you very much.
Thank you, Udo, for your interesting talk. Also, it's nice to see you have made a lot of improvement in terms of Picard pulse instrument, in terms of optic and the mechanics. So let's move on to the last speaker and also our honorable guest, Professor Véronique Tarrant. She is a member of Academician of Royal Academy of Belgium since 2010, and also she is a foreign member of the Paris Academy of Science since 2016. She is the PI of many several European Horizon 2020 projects, like ERC Advanced Grant and the ERC Synergy Grant. And she is also the PI of LAHA instrument for ExoMars 2022 missions to Mars. Thank you, Véronique, to join us. Now the floor is yours.
Thank you. Can you see my slide properly?
Yes, okay. I can see it.
Thank you. So the title of my talk is a little bit bizarre, I think, with respect to the climate theme of this workshop. But you will see, I will not really speak about rotation and interior, but just show you that these ingredients are also important if we want to understand climate and habitability on the long term. So first, let me define what is habitability. So what I mean by habitability is the potential of a moon or a planet, an environment, past or present, to support life of any kind, even if life does not exist. So these are about the conditions to have life. The only example we know is, of course, the Earth. We have life on Earth, and the primitive soup that has led to this life is believed to be the general way to have life. And in particular, what you need for habitability, and these are the habitability conditions, it's to have energy, liquid water, and some nutrients. So these are the three keywords that you need to define habitability. So what you need is energy, liquid water, and nutrients at the surface of a planet or a moon or in the interior, as we will see. But on Earth, we have several geophysical phenomena that are very interesting for having life. Indeed, we have a magnetic field. This magnetic field protects us from radiation, and it protects the atmosphere from erosion by solar winds. So it has an important role as well in the habitability conditions. On Earth, we have plate tectonic with a resurfacing of the Earth and a mixing of what is on the surface and inside the planet. We have volcanism, and this we have on all planets. We have an atmosphere, and this is a very, very nice atmosphere where at present we can breathe. We have a water cycle, and we have liquid water at the surface of the Earth. We have a very nice gravity. We can move without problem. We have a carbon cycle. This is interesting as well. And we have a moon. This satellite stabilizes the orientation of the Earth in space. And we have had, and we still have, impacts of meteorites and comets. This brings volatiles, and it can also take out a little bit of our atmosphere. Again, liquid water appear as central here, and all of this is kind of related to liquid water, and this is what I will show later. First of all, let me show you the diagram, the phase diagram of water, where you have pressure on the one hand and you have temperature. So you know that at the Earth's atmosphere, you're going from liquid water to ice at 0 degrees and from liquid water to vapor at 100 degrees. And this is the temperature that we have on Earth and the pressure that we have on Earth, minus 50 up to plus 50 with a mean of 15 degrees. So of course, here you immediately see that we have liquid water. What about the other planets of the solar system? Let us see Mars. Mars at present. Mars at present has an atmosphere, but the atmosphere is like 7.6 millibars. So it's like 1 over 100 of the atmosphere of the Earth. And so, and the temperature is ranging from minus 150 up to 20 degrees. So you immediately see that you have a lot of ice at the surface of Mars. And really exceptionally, when you are in the middle of the summer, when you are at noon, and that you are not in the shadow, of course, then you can have a little bit of liquid water. But this is really marginal, and on Mars is dry and you have a lot of ice. What about the other planet, Venus? Venus has a very large atmosphere. It's like 92 times the atmosphere of the Earth. And the temperature, the greenhouse effect is very large as well. And the temperature is like 450. So you don't have liquid water neither at the surface of Venus. What about Mercury? Well, Mercury has no atmosphere. So during the night, it's very cold. And during the day, it's very warm. So you see that the only planet that is habitable for the moment is the planet Earth. And the astronomers, they define the habitable zone like the distance from the sun where you can have liquid water at the surface of the Earth. And this is the solar system. We also have a very interesting idea that to have terrestrial planet with water here, so between the sun and Jupiter, this is a whole history that you have to imagine or to really model, like the Jupiter and Saturn entering in resonance, going close to the sun, then entering in resonance, then leaving the place here for terrestrial planet to form. But I wanted to show this slide because there are other objects of the solar system that can be very interesting. And these are the terrestrial moons of the solar system, like Europa, Ganymede around Jupiter, Titan around Saturn. So all these moons, they are terrestrial objects. Of course, it's very, very cold there, but there is a lot of volatile, and so there is a lot of ice, and you have a crust of ice at the surface of these moons. Below the crust, you can have liquid water because entering the planet, entering the moon, the temperature increases. And so below the icy crust, you can have a subsurface ocean. And this is very interesting because you will have liquid water energy. And if the liquid water is in contact with the mantle and crust, you have nutrients. And so these moons are also interesting for habitability in general. This is Europa. You see the icy crust, and below the icy crust, you have a subsurface ocean. This is Enceladus. Enceladus is one of the moons of Saturn that has been visited by the Cassini spacecraft. And here, this is a real image of vapor coming out of the so-called tiger stripes that are that you see here at the surface of Enceladus. But let us come back to the terrestrial planets of the solar system, and let us come back to Mars. We know that Earth has at present water, but at present Mars has no water, or very marginally at some points. But and there is an atmosphere, of course, like here. But if you look at the surface of Mars, you see a lot of traces of water and large fluxes in the past of Mars. You see, for instance, here you have a delta of a river, you have meanders, like here, you have riverbeds, and all these signs, they are mostly in the southern hemisphere of Mars, so where the crust is very, very old. There is a lot of crater, as you can see here. So you have traces of water in the past of Mars. And this is in the very beginning of the solar system, from 4.6 gigayear up to 3.5 gigayear. There you had large fluxes. So that means that this is the graph I had shown before, but that means that instead of having such an atmosphere, such a low atmosphere, in the past, you had a large atmosphere and enough greenhouse effect and pressure to have liquid water. So Mars was habitable in the past, and that's a very interesting, interesting subject. This seems to be a quite complicated slide, but in fact, it's very simple. It's just explaining that there is an exchange between all the reservoirs within a planet. This is Earth. This is planet Earth. And what you have is you have a core which induces the magnetic field. So you have a dynamo action. You have a mantle in which you have convection driving the plate at the surface. You have a crust with plate tectonics, and you have an atmosphere. And this is for Earth. And what you see is that you have exchange between all these reservoirs. You have a dynamo action with a magnetosphere, which is shielding the atmosphere from the erosion by solar wind. You have a crust with subduction, with regassing of the mantle, which changes the volcanism, which degassing from the mantle, outgassing from the mantle, weathering. And with that, you have a nitrosphere, a cryosphere, and the biosphere. And you have also exchange between the biosphere and the atmosphere. So the Earth is quite complicated. It's a planet with tectonic and with all exchange between these reservoirs. And this shows that interior is something very interesting for the Earth. This is Mars at present. Mars at present, the only thing we have is volcanism from the mantle, which could a little bit regaze or degaze in the atmosphere. And you have a large of erosion by solar wind for this atmosphere. Mars in the past had a magnetic field, and I will show you that in the next slide. But this is very interesting. There was a magnetic field in the past, and this magnetic field was protecting the atmosphere. There was a magnetosphere, and so it was protecting the atmosphere, shielding the atmosphere from the erosion from solar winds. And this has happened at the very beginning of the solar system, where we see traces of water at the surface of Mars. And we also, the first thing we had at the very beginning of the solar system is impact. And you have seen that you have a lot of asteroids, and you can bring volatiles. You can bring volatile in the atmosphere, and you can also escape a part of the atmosphere. So there are both trade-off between what impact can do at an atmosphere. You also see that at present, we don't have a dynamo action. We don't have a magnetic field. So we don't have this shielding of the atmosphere. And how do we know that? Well, we measure at present that there is no magnetic field, but we have also measured that in the past, we had a magnetic field. So on Earth, at present, we have a magnetic field, but in the past, when there was a magnetic field, the dike from the mantle and the solidification of mantle material at the surface have imprinted the magnetic field at that time. And what you see is a remnant magnetic field. So a very old traces of a magnetic field from the past. And what you see here is that it's in the southern hemisphere. This is the equator, 0 degree, and this is the South Pole. In the southern hemisphere, where you have very ancient terrain, there you see that there was traces of a magnetic field. So the magnetic field existed from the very beginning of the solar system up to 4 gigayears. So very, very beginning of the solar system. And that is very interesting because at that time you had an atmosphere. You know you had an atmosphere because you have liquid water, at least at some episodic parts in the past. And so the question is related to the title of my talk. It is important to link climate and exchange between all the reservoirs to what is going on inside the planet. And in particular, where are we in the evolution of the planet? Is the core liquid? Is the core solid? Do we have enough motion to induce a magnetic field? These are questions that we have to solve to understand the habitability of Mars. The way we will do that is the following. You have maybe done this. You take a raw egg and a cooked egg, you make them turning. They are turning differently. And here I'll show you a cooked planet on the left and a raw planet on the right. So you see that the orientation of the planet on the right changes a lot, while the orientation, the variation in the orientation of the planet on the left is not changing a lot. And this is a planet with a solid core on the left, and this is a planet with a liquid core on the right. So it's interesting to know when looking at the planet, when looking at the rotation, you can tell something about the deep interior. And that is the way we have access to this information. It's the only way we have access to this information. On Earth, we are doing that since a long time, since the 60s, something like that. On Earth, we measure the Earth's rotation and Earth's orientation using very long baseline interferometry. These big antennas, they are observing quasars, and quasars are objects that are so far away that they don't have motion. So they are like spots in the sky. And so you can really see and obtain the Earth's orientation and rotation in space at the sub-centimeter level. So on Earth, you have a lot of information on the rotation and then a lot of information on the deep interior of the Earth. What about Mars? Well, in order to measure or to have information about the deep interior, we will need to observe the rotation. And the way to do that is to use a system which is called the Doppler radio signal, and we measure the Doppler on this radio signal. And this is what we do with the InSight spacecraft. InSight is a NASA experiment with a lot of instruments like seismometer, which is from, and heat flow measurements, which are from Europe. And here you have two antennas. And we are using these two antennas to measure the rotation of the planet. The spacecraft has been sent and landed on the surface of Mars in November 2018. And so we have now more than 1 Martian year of data, which is really fantastic. And what we do is we use a radio link between Earth and Mars. We send a signal with big antennas like this one on the left. This is the 70-meter antenna. So we send a signal from Earth to Mars. And there we have a coherent transponder. So that's an instrument that sends the signal back to Earth without adding, like a mirror, without adding any phase. And then you can measure the Doppler between the Doppler shift between the planet Mars and the Earth. And with that, you can measure the rotation of Mars with respect to Earth, of course, but Earth, we know it very precisely. And so we are now at a point we are able to measure the rotation of Mars. And I can tell you that we have a paper under embargo that will be submitted next week, I think, where we show that the core of Mars is liquid and a very large core. It's a very large core which has a lot of iron, of course, but a small percentage of light elements. So it's very interesting discovery. In 2022, and I will finish with that, we have another mission that will follow the InSight mission, and that is the ExoMars mission. This is a joint venture between ESA and Roscosmos, so the Russian space agency. And there is one instrument which is on a platform. There is a rover as well that will drill in the subsurface to see whether there is traces of life in the rocks. But there is also some radio science instrument. And this instrument is called LARA. It's a Belgian instrument. So we have small antennas like here that have been done at UC Louvain, so at the Université Catholique de Louvain. And we have a transponder that has been furnished by Antwerp Space. And everything has been delivered. The flight model is on the deck. We still have some tests to perform before the launch. And we are looking forward, of course, to have new data in the future. And with this, I stop my talk and thank you for your attention.
Thank you very much, Veronique.
Okay.
Very fascinating talk, very interesting. And now I think we are late, but I think we still have some minutes for the roundtable discussion. And so we still have two honorary guests that we have not introduced. And the first one is Professor André Berger. He's a professor from University Catholique de Leuven and the honorary president of EGU, and he's an academician of Belgium Academy. And another one professor is Professor Huang Shaopeng from Shenzhen University. Yeah, Ping, do you want to say? You have a few.
Yes, I can give a few words about Professor Huang Shaopeng from Shenzhen University. In fact, he's quite a pioneer scientist to study the global climate change from the Apollo surface temperature measurement. In fact, he studied the temperature of the moon, and he found the reading at a very early stage finds the temperature rise from the lunar surface. And he's also now promoting the using the moon and as a base to observing the Earth's climate change. Thank you, Professor Huang, to join us.
Yeah, it's a
Thank
good.
you for introduction.
Yeah, sorry. We see that in the chat, all the questions raised has already been answered. So it's very good. Now I have a question related to the climate. Yeah, probably it's a question for Professor Berger and Hugo Goss and Dr. Hamdi. So we know that the COP, the Conference of the Parties, are willing to limit the global warming to 1.5 degrees Celsius above the pre-industry value, yeah, before the end of the 21st century. Yeah, we already heard from the talks, a few talks of today. So Professor Belshi, what's your opinion on this? Can we limit this temperature increase? Hello, Andre.
Yes. Okay.
Okay.
It's better now.
Yes.
This COP objective is certainly an excellent objective. Unfortunately, we do not know how to reach it. First, we are already more than 1 degree Celsius above the average of the end of the 19th century, as it has been reminded this morning by Hugo and our colleague from the RMI. Second, many people are speaking about limiting the global warming, but nobody is coming with a serious proposal about how to reduce the CO2 emission, which are at the origin of the global warming. Some are claiming that the solution is in using the renewable energies like wind and solar. But this is false, because it is leading to the opposite effect of what we like to obtain. This is increasing the CO2 emission. These energies are certainly renewable and decarbonized, but they are intermittent and non-controllable. As a consequence, for ensuring the security of electricity supply, gas power plant must be used. But these power plants are emitting 40 times more CO2 than the nuclear power plants for the same energy generation. Not only the nuclear is decarbonized, but it is also much more efficient and cheaper than the gas power plants to provide electricity, and certainly more efficient and cheaper than renewable energies. The solution is therefore in using the actual nuclear power plant, waiting for new nuclear technologies like the small modular reactor of weak power, the so-called SMR. Let me finish by, for answering this question, by reminding you what probably all of us know already, but China is now the largest emitter of fossil fuel CO2, much more than the United States, about the double. But we have heard this morning also that climate change is proportional to cumulative emission. And the United States is still responsible for the largest cumulative emission, followed by European Union, China, and Russia. So for meeting the objective of CO2 is therefore a worldwide problem involving certainly US, China, Europe, Russia, but also we do not have to forget the undeveloped countries which are becoming more and more on the scene because of their population explosion, although we have to accept that the emission of CO2 per inhabitant there is quite still low.
Thank you, Andy. Does anyone else has a comment?
Yeah, so thanks, so thanks, Andre. So if I may add something, I'm probably a bit more optimistic than Andre about the renewable energy, even if we all agree that the intermittency is a problem. There are solutions that start to be developed by storing the energy during sometimes even transforming the energy in hydrogen. There were a plan announced yesterday in Belgium related to the transport of hydrogen. So the nuclear energy is maybe one solution, but I think we will have to use a kind of mixture of many solutions, because the solution is there, but it comes from, it's all the elements of the system, and decarbonization means really changing a lot of things, and renewable energy alone is probably not simple, but there is no simple solution. And there are some plans, even if they are complicated, it's the implementation that will be probably the most difficult part in the system, which is a bit far away from the ends of the climatologists in a way.
Thank you, Hugo. Yeah. I think that probably Ping has something on the.
Yes, I saw there's a questions from Stephanie in the chat to everyone. What she I don't know if you want by yourself. I can read the questions. I also have questions for André. My question is, what is the difference between the habitability research and the paleo-element research?
It is a question for Veronica.
Yes, I think for both of you, you can answer.
Yeah.
They are intimately related. Climatology, paleoclimate on Earth uses very small changes in the orientation of the Earth to compute climate change. Habitability is more general. We can address questions of other planets having changes in the orientation that can be from 0 to 180 degrees and not having, like the Earth, very small changes in the orientation. So they are intimately related. And I think that's why I think we are all working in our institute, same institute, and that's why we can find synergies as well.
Okay. Yes. Do we have any other questions?
Yeah, actually, I had a question for André. What do you think about the future of fusion?
That you have to ask to physicists. I am not at all involved in energy production, fission or fusion. This is the big problem because everybody is in the field of nuclear energy is always speaking about fusion is coming. But we have to postpone all the time because it's a huge technology. And that's why I am speaking about the SMR, which I really feel is much more close to being used for the future, and especially in a transition, because I agree in some way with Hugo that we expect to have one day a decarbonization possible, but or a storage of CO2 and other greenhouse gases. But up to now, nothing. So my concern is, why are the politicians willing to replace a decarbonized, efficient technology like nuclear by another decarbonized, certainly, but totally inefficient way to produce electricity, which are the renewable technologies like wind and solar? That I cannot understand. All the calculation that I have made, and I do not know if other people in the assembly here have taken the patience to make this kind of calculation, came to the same conclusion. For the present day, the best way to meet the COP, it means reducing CO2 emission, is by using nuclear power plant for producing electricity. No, this is concerning only electricity. There are so many other things involved about energy that we do not have to limit ourselves to electricity, but my concern personally is electricity.
Thanks.
Okay, thank you. Thank you. Okay, I think I have a last, because we are quite running out of time. This is the last question I would like to ask Professor Huang, because he is really promoting to using the Earth as a platform to observing, using the Moon as a platform to observing the climate of the Earth. Professor Huang, can you give some comments about that? Because we also heard from Margit, she's doing, low Earth orbit observations. You are muted. Unmute. You are muted. Sorry.
No, it's okay. Yeah, thank you very much.
Yeah, it's okay.
Yeah, it's my great pleasure to join this symposium. I learned a lot. With respect to my involvement with the Chinese lunar program, as you mentioned, that actually I have been promoting the moon-based observation of Earth radiation budget for better understanding of terrestrial climate change. Global warming is certainly a fact, as Professors Gusi, Hamdi, and a lot of people have just described earlier in their great presentation. However, there is still some critical unknowns in our understanding of climate change. As shown, for example, by the large range of the climate sensitivity of 1.5 to 4.5 degree in the latest IPCC report. This seems to be largely due to the lack of a good constraint on the global radiation budget, as already discussed earlier. The objective of the moon-based Earth radiation observation is to fill the observation gap of the Earth radiation from deep space. The near side of the moon is a natural, giant, stable, predictable, and a broad view forever platform for Earth observation. I have no doubt that the moon-based observation will be complementary to artificial satellite-based observation. Professor Harberter has summarized in her presentation as the recent advance. From the unique viewpoint of the moon, I would expect to gain new insights into climate change of the Earth. I'm very grateful to that both the Royal Observatory of Belgium and PMOD World Radiation Center are willing to support this effort. We certainly are looking forward to a fruitful international collaboration on this effort. Now that we have secure funding for our project from the Shenzhen municipal government, we are trying our best to get the needed instrument ready for near future lunar mission, hopefully before 2025. But until the instrument is afloat, you never know when it will be on its way to the moon. So that's something. And in addition to that, to the Earth observation, I am also working with my colleagues in the Chinese lunar community on the in situ resource exploitation via thermal reservoir in the highly insulated lake layer, and in proposing a new heat flow measurement to answer some questions raised by, for example, the analysis of the Chang'e 5 return lunar samples with respect to the origin and the thermal evolution of the moon. And that's pretty much what I have to say at this point. Thank you very much.
Okay, thank you, Professor Huang. I think we are quite, because we still have a closing ceremony in about about 7 minutes. So I think probably we can. Do you have any other questions also from our guests and also from our participants? This will be a last chance you can ask. And the other things that please all of us switch on your camera. We will take a screen group of photos.
Sorry, if I may ask, I cannot switch on my camera anymore. Could you try to do it? It's blocked by the host.
Ah. Yes, yes. Student, can you check this one? What I shared here is the last slide for the about this session, kind of closing. So please notice that we still have a closing ceremony. The room number I put here, so everyone is invited to join the. Yeah, okay, to join the close ceremony. So it will be very short. But it's not in this room meeting, but another one. I put number over there. Please take a note. So thanks again. So in the slides, you see all the speakers of today, this morning in Belgium, and this afternoon in China. Thank you, all of you, to join us. And children, do you have some words to tell to our guests?
Nothing, just thank you to everybody, and especially the speakers, to give a series of very exciting talks, and also to the participants. Yes, thank you.
Yes, thank you very much.
Thank you. It was a pleasure. Thank you.
Thank you very much.
Thank you, the organizers.
Thank you. My pleasure too.
Thank you. Bye-bye.
See you soon. Bye.
Thank you to everybody.
Please come to the close ceremony. Please to the close ceremony. Okay, thank you.
Then we remade the random model according to the outline curve. Then we also